my team, people at Safran Tech, which is the research center from the Safran Group, and people in Bordeaux in France, Aljan Frely and Cécile Dobrinsky, who unfortunately passed away earlier this year. So this work is dedicated to Cécile. So I will present some parallel dynamic mesh adaptation of unstructured grids, mainly tetraedral-based grids. And we would like to apply that to interfaces and fronts. So premixed flames and primary atomization are two good candidates for this type of numerical method. The context of this work is definitely aeronautical engines, even if we can apply all these methods to many other applications. So here on the left you have some aircraft engines, and here on the right you have helicopter engines. So each time the combustor is a very small part of the engine, and it's responsible only for one thing, which is burning all the fuel that enters the combustor. Okay. When you want to design this engine, and especially the combustor, you have two main constraints. The first one is fuel efficiency. Fuel efficiency because you want to reduce fuel consumption, of course, and you want to reduce CO2 emission. Unfortunately, the combustor is not involved in the fuel efficiency, because if you want to work on this efficiency, the global efficiency, you will work on the propulsive efficiency or thermal efficiency. On thermal efficiency, you will simply increase the pressure inside the engine. That's it. At least the pressure ratio. The second constraint is pollutant emissions. So you have regulations, and you have a number of pollutants like unburned hydrocarbons, smoke, carbon monoxide, nitrogen oxides, and this is where the combustion engineer will work. He will try to reduce all these pollutants, even if people from the efficiency here try to increase the pressure ratio. Usually it's very bad for NOx. It's better for CO, but it's very bad for NOx. So the combustion engineer has to devise some new technologies, like ultra-low NOx combustion chambers, where you will burn in lean conditions. Except that if you want to predict what happens in this type of combustor, you will have a lot of work to do, because you have a lot of physics. So here you have a combustor which comes from an aircraft engine. You have the temperature field. You have the injection system here, which is masked. And in this combustor, you have plenty of physics. Here you inject some liquid kerosene, which undergoes atomization. Then you have transport of the spray. You will have evaporation mixing with air, and then combustion. So you have mixing with turbulence. You have thermal exchanges on the walls. You have complex chemistry in the combustor, which has to be modeled if you want to get pollutants. And we've seen with the years that we need unsteady approaches. RANS approaches have failed, especially for pollutant emissions, which means that now people in the industry mostly use large eddy simulation. This is one of the industry where people rely a lot on LES. And our global objective is really to develop high-resolution LES models for these pollutant emissions. So we've been working now for more than a decade on an in-house multiphysics LES solver, which is described here. It's developed at the lab and also in a scientific group in France with 8 different academic labs. We have a number of users. And here is a list of the features of the code. So it uses mostly unstructured grids, tetraedral-based meshes. We have adaptive grid refinement, which I will detail. We solved the low Mach number Navier-Stokes equations with central finite volume schemes. We have a number of models for combustion, two-phase flows. We also have a CFD-DEM solver, and Jan will present that on Thursday. And most important, we try to develop really high-performance computing features in the code, so that we are able to run on more than 32,000 processors on a regular basis. Okay, so now if you have this code, you need to validate it. Except that validating such a code on a real scale combustor is very difficult. Especially for low NOx combustion, we don't have so many of them. So people have been using some academic or semi-industrial academic burners for a while, like the premixed burner. Okay, so this is the burner which will help in validating the solver, the flow solver. So it's a lean premixed methane air combustor. You have the power and the Reynolds number in the burner. So it consists of a swirler, a plenum here, a swirler, and here the combustor. So we have plenty of experimental and numerical study on this burner. It's very well known now in the community. It was really designed to validate LES. So how can we validate? Usually we compare the numerical data to Raman scattering measurements for the measured species and for temperature. The modeling strategy that I will present today is focused on finite rate chemistry, which means that we will transport species and enthalpy. And we use a model which is called the dynamic thickened flame model, because the flame is so thin that we are not able to resolve that on the mesh. So we have to thicken it on the mesh to be able to resolve it. So here is the typical simulation that we are able to perform now, which is one of the biggest one that we performed recently. We have almost 1 billion elements in the burner. We transport 17 species, and we have more than 70 reactions. And then here we use non-adiabatic walls, which means that we have heat loss on the walls, and this is very important for the flame, for the topology of the flame. So here you have a rendering of the flame, of the heat release in the combustor. Here you have the velocity field, so it's very particular. You have some very big recirculation zones here inside the burner, and you have also corner recirculation zones. This is due to the fact that the flow is rotating quite strongly, and so you have all these recirculation zones. Here you have the methane mass fraction, the temperature. Here you have the CO mass fraction. So this is the main pollutant that we will be interested in. Here you have the OH species, OH radical, sorry. And here you have the heat release in the burner. So as you can see, we have a flame only in the inner recirculation zones. We don't have any combustion in the corner recirculation zones. And this is something which is very important here. So we've done plenty of studies on this burner. The most recent one was a mesh refinement study for this non-adiabatic condition. So here you have the flame structure. So this is an isosurface of the progress variable here, .7, for 4 different meshes. So here the meshes are detailed here. We go from 1.7 million cells to almost 1 billion, okay? And we have a mesh resolution here of 150 microns in the reaction zone, which has to be compared to more than 10 centimeters for which is the width here of the burner. So as you can see, when we increase the mesh resolution, we have more and more resolved wrinkling, which is expected. What is not really expected is that the liftoff of the flame in the outer recirculations here, it evolves with the mesh resolution. On this mesh here, we have almost no heat release in the corner recirculation zones. Okay, and this is not the case on the coarser resolutions. So it's very bad news. It's bad news because it means that our models are not able to predict correctly the flame topology on this coarse mesh resolution. And we know that this finest mesh resolution is correct because we can compare all this data to the experiment. And when you compare to the OH radical measurement, you can really see that we have very similar topologies, and we don't have any OH in this corner recirculation zone as in the experiment. If you go with the adiabatic condition, you have a flame in the outer recirculation zone. So definitely we need to have this heat loss in the calculation to have the correct results. So let's now look at this pollutant, the CO mass fraction. So here we have a comparison of for different profiles here that are taken inside the combustor at different distances from the head of the combustor, and you have the 4 different mesh resolutions compared to the experiments. So here you have the squares or the experiments, and here you have the 4 different mesh resolutions, the increasing here of the resolution. So the good news is that with the highest mesh resolution, we are very close to the experiments compared to all the data, the numerical data that have been accumulated over time. These are this is the best agreement that we've been able to get with all these numerical studies. The bad news is that with the very coarse resolution, we are very far from the experiments. So it has different origins. The first one is the combustion model that we use. We thicken the flame, as I said, and this is very bad for the minor species like the pollutants, like CO mass fraction, because when you thicken the flame, you increase the amount of CO that you have in the burner. So we have definitely a combustion model effect, which can be seen here. And we have another effect, which is the extinction of the external flame. We don't have any extinction of the external flame on the coarse mesh resolution, so we have a very big peak here. Okay. And when we extinguish the external flame, when we increase the mesh resolution, then we get something which is far more realistic in the outer recirculation zones. Okay, I won't spend too much time on this combustion part. It's just to show that we need really high mesh resolution. We don't have the models that are correct for the moment to model this phenomena. So the question is, how can we bring this type of simulation and this kind of resolution to the industry, to the industrial users, and eventually, at the end, being able to do a DNS of this type of burner. Because of all the calculations that we perform, we now have an estimation of the amount of CPU time that we need. Here we need something like 4 million CPU hours to perform the calculations that I've shown. Okay, we transport these 17 species, 72 reactions, so it's a lot. We could also increase that. If you take the GRIMEC mechanism, we can go to 53 species and more than 300 reactions. It's quite a lot, but it could be done. But what we want to do definitely is to increase the mesh resolution. If we increase the mesh resolution to 50 microns, then we have a sort of DNS, because we will be able to resolve only flame turbulence interactions in this case. We know what are the different characteristic length scale of the burner, and we know that at 50 microns it could be called DNS for flame turbulence interactions. But if you want to resolve all the species in the scheme, then 10 microns is needed, or even less. People in the combustion community call DNS usually when we are 2 or 3 microns at atmospheric conditions like that. So here I put an estimate of the number of cells that we would need in these calculations and the amount of CPU time. So here 400 million CPU hours, which is sort of unrealistic for the moment. 13 weeks on 200,000 cores, maybe, but it would be very, very expensive. Okay. So we definitely need an alternative to reach DNS faster, or at least to increase the, let's say, the predictability of the model in these cases. So one possible way is to go to something which looks like AMR, because we will use only tetraedral-based meshes. Okay. We are very familiar with tetraedral-based meshes because we don't have any direction. It's really isotropic. So this is something that we like a lot. And all the finite volume method that we have are based on tetraedral-based meshes. Okay. So what we would like to do is this type of calculation. Okay. We have a flame front here. We have a collapsing flame. And we would like to be able to put all the cells just where we have the flame front. Okay. To maximize the efficiency of the calculation. Of course, if you have turbulence here in the fresh gases, then you will need to put also cells inside the fresh gases here. Okay, so maybe we will need several criteria to adapt the mesh where we really need that. Okay, something if you put cells just at the flame front location here. You can see that the mesh is static where you have the flame front which propagates. Okay, so the flame in fact sees a constant mesh where it propagates. Okay, the mesh is adapted after and before the flame, but not at the flame front location. So this is something very important because it means that we don't have any interpolation errors at the flame front location. Okay, so that's the strategy that we would like to develop. So we've been working on that for 4 or 5 years now, and the first the first component that we need to do this type of calculation is to have an edge adaptation library for TETs. So edge adaptation means that for tetraedral-based meshes, that we will need to do a node insertion, we will need to swap edges, faces, do element collapsing or edge collapsing, so plenty of topological modifications of the mesh. This is not something that we wanted to develop in the code, so we checked that all the open source libraries that exist to do this type of operations. The first one here is the one that we chose because it is developed by people in Bordeaux that we know very well, and it has very nice features like ensuring the quality of the elements. We have a very nice control of the skewness of the elements, and this is very important for the numerical method, the finite volume methods that we use. Except that this library is sequential; it's not parallel, so we'll need to do something on the parallel side. So the strategy that we designed, which is published in this paper, is based on a two-level domain decomposition. It means that here, if we have a mesh, we have a first level of decomposition, which means that of domain partitioning, the mesh is split into partitions, and the number of parts that you have is a function of the number of processors that we have. Okay, and inside each processor, we'll divide again the mesh into cell groups. Each cell group has something between 500 or 1,000 elements. It was designed first to have very good memory accesses, okay, to avoid any cache misses with the processor. So it was designed just for performances initially, but this is something that will be really essential for the parallelization here of the adaptation. So this is the example. So what is the strategy? We start from this mesh. First, we remove the cell groups. That's a pity, but we have to remove them to adapt all these big blocks here. We adapt each block without touching the interfaces here. Else, we would have to rebuild some connectivity in parallel, which is very difficult to do. So we'll do the adaptation on each block here with constant topology at the interfaces. We check the quality. If the quality is not correct, we can restart this procedure here. Then we do the interpolation of the mesh of the data from the old mesh to the new mesh, and then we do splitting. So you can see that here we have blocks that are not the same as the ones that we had before. And then we do constraint load balancing, which means that some of the cell groups that are here at the interface will move, so that the interface between two processors here will be here at the next step, and this interface will be adapted at the next step. Okay, which means that we need several steps to do a mesh which is fully adapted. The good thing is that the mesh is always load balanced. The number of cells that we have per processor is always the same. So this is a good quality of the procedure. And here, the only input that we need to give to this strategy here is what we call the metric, the isotropic metric, which is equivalent to the desired local cell size. So in practice, so this is an illustration of all this strategy. We start with a certain mesh. We give this metric, so we want to refine on a sphere. So what happens after the first step? We have this type of mesh. You can see that we have some defects in the mesh. This is where the interface between two processors is located. Okay. Then we move the cells that are around the interface, and then we adapt the mesh again. So you can see that here the defect has disappeared. This one is still here because it's at the intersection between two interfaces, the old one and the new one. And then simply repeating this procedure, then you have something which is adapted everywhere. Okay. So that's what we developed, and now we let's say two years ago we started to do plenty of applications with this type of method. We also optimized a lot how to exchange the cell groups from one processor to another. So we have now very good performances. Very recently, we started to apply that to this Prekinsta burner. So here we simply refine the mesh where we have the flame. The base mesh is the second one, with 40 million cells and a mesh resolution of 600 microns. And here, with this procedure, we have the same resolution as this mesh here, which means that we have 300 microns at the flame front location. Okay, the mesh that we have here during the adaptation is 38 million cells, which means that it's roughly 3 times lighter than this one for the same resolution at the flame front location. So we have normally here a speedup of 3. In this case, in fact, the adaptation costs almost nothing compared to the transport of 17 species and all the finite rate chemistry. So this is really the speedup that we have at the end. Of course, the speedup can increase if you increase the resolution at the interface. Okay. So that's one example for combustion. I have only another example for combustion. People in the industry started to use that for ignition of combustors, because this is definitely a case where you need to put a lot of cells where you have the ignition kernel. Ignition kernels, when you study ignition kernels, you have a critical radius of ignition, which depends in LES directly on the mesh resolution. If the mesh resolution is too coarse, then you may have a misfire just because of numerical reasons. So here we increase a lot the mesh resolution just where we deposit the energy. And here we refine the mesh 5 times in each direction. So we go from 41 million cells to almost double. And this is something that runs during 5 hours on 500 cores. So this is something that really can be done in an industrial context. But another candidate for this type of dynamic mesh adaptation is definitely primary atomization, because you have a lot of dynamics that happen at the interface. You have people in this room that know that very well, like Stefan. So it was a very good candidate. And we started a while ago on jet in cross-flow configurations. So you have a picture here of one of our simulation. So here you have primary atomization of the liquid core. Okay, so sorry, you have an airflow coming from the left, and you have here some liquid injected from the hole here. And so you have primary atomization in this region, and here we have sometimes secondary, what we call secondary atomization. Okay, the droplets will break up into smaller droplets. So the configuration that we wanted to study is the one of Ragucci et al., which was published in 2007. This is a high-pressure kerosene jet, which means that the pressure inside the experiment here is 10 bars. You have the air velocity and the kerosene velocity. So we have Weber numbers that are, we have 2 different operating conditions. The first one, the Weber is 60, and for the second one, it's 400. And here you have the 2 momentum ratios that we obtain. In terms of numerics, we use the Gauss-Fluid method. We use also the accurate conservative level set that we developed with Olivier a while ago. It can be easily generalized for unstructured grids. We have a constant cell size at the interface. So it means that the mesh, the metric will be defined as constant really at this interface location. And we have a linear evolution of the cell size away from the gas liquid interface. So in the code, the mesh will evolve like that. So you can see the constant mesh size at the interface and the adapting mesh elsewhere. So this is the type of calculation that we get. Here we are at 10 microns at the interface. The mesh ranges from 28 million cells at the early beginning of the simulation without any liquid, and we go up to 600 million cells at the end when we have almost 8,000 small droplets here. It was run in between 6,000 and 10,000 Broadwell cores on a machine at CEA in France. And you can see all the details that we are able to capture with this method. This is the cell size, in fact, that we prescribed for a coarser case, just to illustrate that, in fact, the mesh is really refined only where we have the droplets. So you have to imagine that when the droplets move here, you have all the mesh which is really adapted here and refined just at the interface location. So we performed a small sensitivity study. So we have these two cases here are for the first operating conditions. Here you have the second operating condition, and you have two mesh resolution, 20 microns and 10 microns each time. So you can see that we have really two different regimes of breakup. We have column breakup in this case. Here we have more surface breakup after some distance here of the liquid injection. We have far more droplets when we increase the mesh resolution, which is expected. And more interestingly, we performed some quantitative comparisons with the experiments on jet penetration. So we perform exactly the same analysis as the experimental one, meaning that we take single frames here, we average them, and then we find the limit here of the contour, of the mean contour of the scalar here, which says that the interface is at a certain location. And here you have the comparison between the correlation that was determined experimentally by Ragucci and the calculations. And we can see that increasing the mesh resolution leads to better results in this case. For the second operating conditions, we have almost the same jet penetration for the two cases that we computed. A final comparison was obtained, in fact, by looking at the jet breakdown. So this is something which is very difficult to determine experimentally. So what Ragucci did is to compute a sort of variance of the height of the interface, and performing an exponential fit on this variance. And when this variance increases quite rapidly, it will be the point where you have the jet breakdown. And so, performing the same in the calculations, we were able to compare our results to the experiments, and you can see that we have some good agreement with the correlation of Ragucci. So it's very encouraging. So we still have to look at plenty of other details, like the size, the droplet size distribution and stuff like that. We don't have that for this experiment, so we are computing another one just right now. A final example before concluding, people in the industry start also to use this type of method for pressure swirl atomizers. So pressure swirls atomizers, so you have here a real system which is used in an engine, and here you inject the liquid kerosene inside small channels here that will make it rotate, and then you have the formation of a hollow cone inside the combustor. So here you can see a 3D view of the interface, and here you have a 2D cut of the mesh, and you can see what people can do now with this type of method. So you have the liquid sheet really entering the combustor and starting to atomize. We are still doing some analysis on that. It runs on 1,000 cores, so it's quite reasonable now. So just to conclude, I've shown that we were able now to do LES of complex burners with finite rate chemistry. It's quite expensive, but if we can couple that with dynamic mesh adaptation, we will probably be able to do some substantial gains. There are plenty of theoretical and numerical developments that are still needed. I talked about turbulence, but when you do LES, you know that if the filter size changes over time or space, you introduce space and time commutation errors. This is something that has to be studied here because we have some very sharp gradients of the cell size and the filter size. We need also to to couple that to surface remeshing, because if you have some liquid films on the walls of the combustor, you probably need that. So this is something that we've been starting to do in the team. So you have some examples here on the sphere, and since I have students with a lot of imagination, they also try to do some adaptation. So maybe you know this very famous French singer, Johnny Hallyday. Okay. Yeah, from Los Angeles. Thank you very much for your attention.